projects. In this video, we are going to explain about the project entitled as Fast Detection and Classification of Ink by Ion Mobility, Spectrometry and Artificial Intelligence. So before getting into the video, let me give you the brief description about the project. The project aims to quickly identify and categorize different ink types using ion mobility spectrometry IMS, which analyze the chemical fingerprints of ink. Artificial intelligence is then applied to these spectral patterns to automatically classify the inks with high accuracy. This approach is fast, reliable, and useful in forensic investigations, document verification, and quality control in printing industries. Coming to the abstract of the project summarizes the development of a fast and precise system for detecting and classifying ink using ion mobility spectrometry combined with artificial intelligence. IMS generates a unique chemical fingerprint for each ink by separating ions based on their size, shape, and charge, capturing the distinct composition of different inks. AI algorithms then process these fingerprints to automatically identify and categorize the inks, eliminating the need for manual analysis. This method offers significant improvements over traditional techniques in terms of speed, accuracy, and reliability, making it highly suitable for applications such as forensic investigations, document authentication, and quality control in printing process. Coming to the existing system for ink detection and analysis relies on traditional techniques such as thin layer chromatography, high preference liquid chromatography, UV visible spectroscopy, and Raman spectroscopy, which provides detailed chemical information about ink samples. However, these methods are often time-consuming, costly, and require trained personnel to perform and interpret the results. In some cases, ink identification is done through visual inspection or manual comparison, which is highly subjective and prone to errors. Overall, this existing system lacks automation, process data slowly, and are inefficient for handling large data sets, making them less suitable for rapid forensic investigations or industrial applications where speed and accuracy are crucial. Coming to the proposed system or base paper work, the proposed system integrates ion mobility spectrometry and artificial intelligence to create a fast, accurate, and automated solution for ink detection and classification. In this approach, ink samples are first ionized and analyzed using IMS, producing a unique mobility spectrum that serves as a chemical fingerprint for each ink. Machine learning algorithms are then trained on these spectra to automatically identify and classify new ink samples. This method is rapid, delivering results in minutes, non-destructive, and requires minimal human intervention, making it more efficient and reliable than traditional techniques. It is particularly useful for forensic document examination, detecting fraud signatures, and ensuring quality control in print and related industries. Coming to the dataset, the Spectra ink sample dataset from Kaggle provides spectral data for dataset ink samples and is specifically designed for detection and classification using machine learning and AI. Each row represents a single ink sample, while the columns contain spectral features such as ion mobility intensives or readings at different time intervals, which acts as input variables of AI models. One column specifies the type or class of ink, serving as a target label or supervised learning. This dataset is valuable for building automatic ink recognition systems in applications like forensic document analysis, fraud detection, and printing quality control. It allows researchers to perform data pre-processing, feature analysis, model training, and evaluation, enabling fast, accurate, and automated classification of ink types. Coming to the novelty or extension or enhancement or improvement. To enhance model performance, interpretability, and user interaction, first, outliers were removed from the dataset and random forest-based feature selection was applied to identify the most important features improving the efficiency and accuracy of the model. Using these selected features, a stacking classifier was trained with extra trees and XGBoost as based estimators whose hyperparameters were tuned and logistic regressions as the final estimator, achieving the highest accuracy of 97%. Additionally, explainable AI techniques like LIME and SHAP were used to interpret the model predictions by highlighting the importance of individual features. Finally, a Flask-based user interface was developed allowing users to input data and obtain predictions from the trained model, making the system interactive and user-friendly. Coming to the flow of the work, first, we need to import the packages. In this module, all necessary Python libraries and packages for data handling, visualization, and machine learning are imported to set up the environment for the project. Next, exploring the dataset. The Spectra Inc. samples dataset is examined to understand its structure, types of feature, target labels, and general characteristics, providing insights for pre-processing and modeling. Next, data pre-processing module. Data pre-processing involves cleaning the dataset by removing null values and duplicate entries to ensure consistency and accuracy in the analysis. Next, label encoding. Categorical string values in the dataset such as ink types or brands are converted into integer labels, making them suitable for machine learning model. Next, data visualization. Visualizations are created to explore the data, including brand distributions, confusion metrics, UMAP, and MDS, helping to understand patterns and relationships among ink samples. Next, PCA feature importance. Principal component analysis is applied to identify the most significant features contributing to the classification of ink types. Next, train test split. The dataset is divided into training and testing sets, ensuring that models can be trained and evaluated on separate data for unbiased performance assessment. Next, build the classification model. Multiple classification models are built, including decision tree, random forest, extra tree, gradient boosting, KNN, SVM, and passive aggressive classifier. Grid search CV is used to optimize hyperparameters and enable models like outing classifier are employed for improved performance. Coming to the extinction, outer layers are removed. Random forest based feature selection is applied to retain important features, and a stacking classifier is trained with tuned extra tree and XGBoost and base estimators and logistic regression as the final estimator. Next, training the model. The selected models are trained on the pre-processed training dataset to learn patterns and relationship between features and ink types. Next, model evaluation and comparison module. Trained models are evaluated using metrics such as accuracy, precision, recall, FN score, and AUC ROC. And comparison graphs are generated to visualize the performance of all models. Next, save the best model. The model with the best performance is saved for future use, enabling fast predictions without retraining. Next, explainable AI techniques. Techniques like LIME and SHAP are used to interpret the model's prediction, showing which features contribute most to the classification of ink samples. Coming to the front end, a Flask-based front end is developed with the user registration and login using SQLite. Users can input features which are pre-processed and fed into the trained model, and the prediction outcome is displayed interactively on the interface. Algorithms used in the project are hyperparameters are decision tree, random forest, extra tree, grid search CV with hyperparameter like decision tree, random forest, extra trees, gradient boost, KNN, SVM, passive aggressive classifier, and a voting classifier which combines decision tree, extra tree, and random forest. As an extension, we remove the outliers, random forest based feature selection, and stacking classifier with tuned hyperparameters including extra tree and XGBoost. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consisting of operating systems, Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework is Anaconda, primary language is Python, Front-end framework is Flask. Backend is Jupyter Notebook. Database is SQLite 3. Technologies which we use to build the front-end are HTML, CSS, JavaScript, and Bootstrap 4. To execute this project, first, we need to open the code folder, which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are the model files which contains algorithm information which will be loaded into the project code during the runtime. Notebook.ipynb file. This is a Jupyter Notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Next, signup.db file. This file is a database file used to store the user information. Now, coming to the execution of the project, firstly, you need to copy the path from the address bar of the file explorer. Then, open Anaconda prompt. Use the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the local link provided by the framework and paste it into any web browser. I prefer Chrome. This is the home page of the project, should now be displayed in the browser. This is a front-end built using Flask framework. In this page, we have home button and register button. Now, click on register button so that the logon HTML will be opened, where you need to give the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. Then click on create an account so that all the given details are stored in signup.db and the login.html will be opened, where we need to access the application by username and password. Then click on sign in so that the prediction page has been displayed. In this page, we have home button, ink classification button, data visualization button, notebook button, and logout button. Firstly, click on ink classification button so that the IMS spectral feature input form will be opened, where you need to enter the ion mobility spectrometer spectral feature values to classify the ink type using our advanced AI models. Each feature represents a specific measurement point in IMS spectrum. Now, let us check one by one giving the inputs. As we are using ball pen, gel, and oil pen, let us check for 3 inputs. First, let us go with ball pen. Color is black. Measurement is 24. Spectrum will be 256.145131314141. Spectrum is 133. Point 127 is 256.145131314151. Point 322 is like 493.008614009156. Point 334 is 476.993943819476. Point 608 is like 82.1 34230 8858686. 0.616 value is 132.530918903772. 0.649 value is 210.130063230691. 0.662 value will be 151.241169511135. 0.667 value will be 262.108625691341. Now click on Analyze with AI. So the input values are pre-processed and the output is displayed as predicted ink type is pilot. Confidence level is 99.9%. We also have the information like about the result, about pilot, analysis method, forensic applications and important notes. So now let us click on classify another sample. Now let us check for gel pen. Color is black. Measurement is fresh. Spectrum number is 4. 0.127 value will be 197.6598854352299. 322 value will be 357.812144949657. 334 value will be 365.7336208228281. Next 0.608 value will be 290.0084520836376. 0.616 value will be 299.2489498107886. 0.649 value will be 266.674783534866. 0.662 value will be 204.585397481657. 0.667 value will be 266.852806428234. Now click on Analyze with AI. So the input values are pre-processed and the output value will be displayed as M and G. The predicted ink type is M and G. The confidence level is 99.6%. We also have the information about the results, about M and G, the analysis method, forensic application and the important notes. Now click on classify another sample type. Now let us check the pen type is oil. The color will be black. Measurement is 24th. Spectrum number will be 89. 0.127 value will be 276.69180377207. 0.322 value will be 165.058075590775. 0.334 value will be 122.56038712812. 0.608 value will be 14.34593436438082. 0.616 value will be 61.0985294998298. 0.649 value will be 66.2213337874159. 0.662 value will be 104.926122480667. 0.667 value will be 146.9812051355401. Now click on Analyze with AI. The input is pre-processed and output is displayed as cello. The predicted ink type is cello. The confidence level is 99.9%. We also have the information about this result and about cello analysis method, forensic applications, and important notes. And now let us click on data visualization so that the graphical representation of the project will be opened. Let us check one by one graph. First, we have brand distribution graph. This bar chart represents the count of samples for each pen band in the dataset. Some brands have noticeably higher count, indicating they are more frequently represented. Others have lower but still consistent representation. Understanding this distribution is important for identifying class imbalance that could affect modeling or analysis. Next, we have PCA graph. This graph illustrates how much total variance is explained as a number of principal count components increases. A step rise at the beginning indicates that the first few components capture most of the data's information. After a certain point, adding more components yields dismining results. This plot is useful for deciding the optimal number of components to retain in dimensionality reduction. Next, we have correlation matrix graph. This heat map shows the pairwise correlations between different variables such as pen type, color, and multiple spectral points. Strong positive correlation indicates variables that move together, while strong negative correlations indicates inverse relationship. Clusters among spectral points suggest redundancy or similarity in those measurements. This helps identify which features may be strongly related or potentially reduced. Next, we have UMAP projection graph. The UMAP plot provides a 2D visualization of high dimensional feature embeddings. Each cluster represents a different class, and the clear separation between clusters indicates strong feature representation. Minimal overlap suggests that the classes are well defined and easily distinguishable. This supports a higher accuracy and ROC performance observed in the previous graph. Next, we have confusion matrix and ROC graph. The confusion matrix visualizes how well the stacking classifier predicts each classes. Most values are concentrated along the diagonal, indicating a higher number of correct predictions for each brand class. Only a few off diagonal enters appear, meaning misclassifications are relatively rare. This confirms the strong and balanced performance of the stacking model over classes. Next, we have multiple class ROC curve graph. The multi-class ROC curve shows the trade-off between false positive rate and true positive rate for each classes. Almost all curves lies very close to the top left corner, which indicates excellent class separability. This suggests that the stacking classifier is highly confident and effective in distinguish between multiple classes. Overall, the model demonstrates near perfect discrimination ability. Next, we have accuracy graph. This bar chart compares the classification accuracy of different machine learning models. It shows that ensemble-based approach like stacking classifier, gradient boost, and extra tree achieves the highest accuracy. Simpler or linear models such as passive-aggressive perform noticeably worse. Overall, the graph highlights how model choice and ensembling significantly impact performance. Next, we have precision graph. This graph illustrates how accurately each model predicts positive outcomes. Stacking classifier, gradient boost, and random forest demonstrate high precision, meaning most of their positive predictions are correct. Extra tree and passive aggressive have comparatively low precision, leading to more false positives. High precision is important in scenarios where false alarms need to be minimized. Next, we have recall graph. The recall graph highlights each model's ability to correctly identify positive insights. Stacking classifier, extra tree hyperparameter, and random forest shows very high recall, meaning they miss very few actual positives. In contrast, passive aggressive has noticeably lower recall, indicating it fails to capture many true positive cases. Models with high recall are especially useful for missing a positive case is costly. Next, we have F1 score graph. This graph compares the overall balance between precision and recall for each machine learning model. Models like stacking classifier, gradient boost, and random forest achieve the highest F1 scores, indicating strong and well-balanced performance. Passive, aggressive, and extra tree models shows lower F1 scores, suggesting weaker overall classification effectiveness. Higher FN scores implies better reliability when both false positive and false negative matter. Next, we have ROC AUC graph. This bar chart compares the performance of different machine learning models using the ROC AUC metrics. Higher bars indicate better ability to distinguish between classes. Models such as gradient boost random forest, SVM, voting ensemble, and stacking classifier show very high ROC AUC values, indicating strong performance. In contrast, simpler or less tuned models have slightly lower scores, highlighting the benefit of ensemble and advanced methods. And next we have explainable AI SHAP graph. The SHAP summary plot explains how different features influence the model's prediction for BIC. Each row represents a feature ordered by overall importance, and each dot shows the SHAP value for one data point. The x-axis indicates whether a feature increases or decreases the prediction, while the color shows the feature values. Features like 0.662, 0.334, and 0.332 have the strongest impact, meaning they play a key role in the model's decision. Next, click on Logout. So finally, the project successfully demonstrates an efficient and automated approach for identifying different ink types. By combining ion mobility spectrometry for generating unique chemical fingerprints with artificial intelligence for accurate classification, the system achieves high speed and reliability. Advanced machine learning and ensemble techniques further enhance performance, while explainable AI improves transparency. Overall, the project provides a practical and scalable solutions for forensic analysis, document authentication, and quality control applications. So this is all about your project. Thank you.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.